Hello everyone, my name is Sungwook, working at Korea Astronomy and Space Science Institute, and today's talk title is the Revealing the Local Cosmic Web from Galaxies by Deep Learning. So when I say about the local universe, that means the universe within a few or tens of megaparsec. So why local universe is important from the beginning? Well, the first thing is that local universe is by definition that we live. So understanding the local universe means our environment came from and how it evolves and how it will be in the future. So for example, what this figure shows about what our local environment will be by showing some simulated night sky. So here now we have the Milky Way galaxy here and very small Andromeda. Many people believe that it will collide in the far future. So as time goes on, Andromeda galaxies come closer and they collapse, they merge, and they make the very one larger galaxy. So understanding the local universe will show what this kind of thing will actually be. Another thing is that understanding the local universe may cosmologically be also very important. For example, nowadays the cosmology has the very significant problem so-called Hubble tension. That means the observation of the Hubble parameter by using the cosmic standard candles and also the Planck or CMB observation has the very significant deviation each other. Some people suspected that probably the local motion of our environment may be related to solve this kind of a Hubble parameter estimation tension. But to understand whether this is really correct or not, then we need to understand the local universe quite exactly. So, but the reconstruction of this dark matter distribution of the local universe is not completely new. Some people has attempted with this kind of thing before, but there are some of the technical difficulties. So the usual the local universe reconstruction has been done first by using the full sky observation of the galaxies. But even the full sky observation will be incomplete because they're observing all of the entire sky where is not easy, and also where the inside in the center of this sky, where there is the Milky Way galaxy. So there are some of the region that we cannot see the external galaxies quite well in the low galactic latitude. Even if we observe the galaxies, still the reconstruction of the matter is quite tricky because the galaxy is the bias tracer of the underlying dark matter. So to most of the people would reconstruct the Gaussian dark matter density by using some of the smoothing of the galaxy field. Usually with that scale is over the several megaparsec scale. Then they add some of different realization of the small scale because small scale is also important to reconstruct this kind of a galaxy distribution. So they run the simulation and they find the best realization among different small scales that fits best with the local environment. So all of these scales, all of this procedure contains very difficulties and also some tricky part. Our aim is instead of doing this kind of incomplete and tricky estimation, we would like to apply the deep learning image reconstruction by directly using the galaxy distribution and to the underlying dark matter distribution by adopting the low galactic latitude masks too. So first, we apply the observation data and we use the Cosmic Flows free galaxy catalog. One good thing of the Cosmic Flows free galaxy catalog is that it provides not only the line of sight velocity from the redshift, but also it provides some distance. So we can use both the distance and the line of sight velocity. That means that we can also apply the peculiar velocity by subtracting line of sight velocity with a Hubble flow. So we use the 40 megaparsec per h cube volume with a 0.3125 megaparsec per h resolution. That means that we divide the volume into 128 cube grid. And we exclude the region close to the galactic plane so that we can match with the observation. And for a fair comparison between the closer distance and the far distance, we apply absolute B-band magnitude cut. Here we apply the minus 16 magnitude. For the training and validation of the deep learning, we use some data what we know is the answer, both the galaxy distribution and the underlying dark matter. So we use the hydrodynamic simulation, so-called illustrious TNG. So here we use two kinds of key selection criteria, which matches with the observation. First, the origin of each subset volume is not randomly selected because we know we are at the center of the observational range. So we put the Milky Way-like galaxies with some sort of the stellar mass range similar to our own Milky Way galaxy. And also we selected the galaxies outside of the origin by using the same B-band magnitude cut and also same galactic latitude mask. So fiduciary simulation, we used the so-called TNG 301. It has a 205 megaparsec per h box size and 2,500 cube dark matter and gas particles. So we use the resolution correction with the galaxy number density cut so that whether we can match the B-band magnitude and also stellar mass or comparable to the observation. Then we use the so-called unit-like convolutional neural network to estimate the dark matter density. So here we use the two channels of the input. So one channel contains the number of the galaxy per each voxel, and another channel contains the averaged radial direction of the peculiar velocity. So here the unit-like CNN would correspond to the two stages. One is called the decoding session, and another one is the encoding session. So first session will increase the number of the channel by decreasing the size of the spatial dimension, spatial size. Then in the end, the another session will increase the size of the volume by reducing the number of the channels so that it will match with the upper layer. Also, to prevent the loss of the small scale during the convolution and deconvolution, we use the concatenation so that we can use the data from this stage directly into this stage. We use around 10,000 training samples and 1,000 validation samples, and we use the loss function by the comparison of the log normalized for the value of the dark matter density with the MSE loss function. And we use the TensorFlow 2 with a Keras framework tool, and to run 200 to 400 epochs, and it takes 3 or 4 days with NVIDIA Tesla V100 card. So this is the brief summary of our performance test. So this column shows the actual dark matter distribution from the illustrious TNG simulation. And these two columns shows the number of the galaxy in each voxel and the average radial peculiar velocity of the galaxies in 3 different dimensions. And this last column shows the estimated dark matter distribution by using these two information as the input by using the deep learning. So by comparing this truth value and this prediction, then we can find that although there is some small difference in very, very small scale, but with the large scale structure, and especially this cosmic web with the scale of a few megaparsec is well reconstructed. One important thing is that if we compare our result with another deep learning architecture that uses only the number of the galaxies, but not using the radial peculiar velocity information, then our best results will look something like this. in very, very large scale, for example, whether seeing the overdense region and underdense region, then it is somewhat similar, but this will surely whether cannot reproduce for the cosmic web in the megaparsec scale. So that means that this peculiar velocity information is very, very important to reconstruct the small cosmic web structure, whether in reconstruction. So this is because the peculiar velocity is not randomly chosen information, but peculiar velocity is related to the motion of the dynamic motion of the system, which is also related to the gravitational potential, and which is also related to the dark matter distribution inside this universe. So not only the number of the galaxy, but also radial peculiar velocity information was very important to reconstruct at this small scale. So this is the sum of the performance tests. So here the left panel shows the pixel-to-pixel comparison between the truth value and the prediction value. So we can see that there is some of the magnitude limit. So this is some of the cutoff in the dark matter density estimation. So we suspect that this might be related to the magnitude limit that we have used for our simulation. And also this is the comparison of the two-point correlation function between the truth and the prediction with a 1 sigma certainty range, and they measured quite well. And this shows the our estimation bi-directly with the updated to the cosmic flows free data. So we can see the very well-known clusters and the galaxy groups information, and also we can see clearly the cosmic web information. So this is our final result by applying our deep learning architecture to the observed cosmic flows free data set. Uh, this is the 2D radial direction projection or sky projection of our result by using several according to 4 megaparsec per h the radial beam. And so each dot and point, and this text shows about the known points of the galaxies and also the galaxy group clusters, and they matches quite well as expected. So here we can also show how the deep learning result by using only the position, not using the peculiar velocity, will differ from this one. So as we can see, the galaxy position matches well, but this cannot predict the cosmic web structure with a megaparsec scale. Unfortunately, cosmic flows 3 data has the sum of the distance error in their distance measurement. So we needed to apply how that will affect our result. So we created 1,000 sets of the cosmic flows 3 catalog by applying normal random distribution of the luminosity distance modulus. So we recalculated the peculiar velocity by using that distance error and apply to our deep learning result. So this is how it will affect our result, especially by applying the sky projection. So the first column shows the average over 1,000 realization, and this is the standard deviation. So they met so mean value is much greater than the standard deviation. So average signal to noise level is greater than 4.5 sigma. So that means the structure is quite well reserved, at least in the sky projection. Also, we compare this to the other cases. We calculate the systematics, because whether we Up to now, we have relying on our training and validation by using a certain hydrodynamic simulation setup. So we changed it and how it affects to our result. So we changed the spatial resolution, and also we changed the assumption on the Hubble parameter. We changed the B-band magnitude cutoff, or training without the peculiar velocity, and using the stellar mass weighted with the position rather than just the number of the galaxies, or just using the dark matter only simulation. But all of these cases, the systematics does not depend much on the actual values. Yeah, so systematics is just within the standard deviation in most cases, and does not affect our result quite well. So in summary, deep learning can reconstruct the dark matter density and the potential of the local universe from the galaxy distribution, and our result is consistent with different box size in the simulation setup. So even with distance measurement error, the 2D projection shows reasonable mapping with the average signal-to ratio of 4.8 sigma, and using peculiar velocity is crucial for reconstructing a few megaparsec scale cosmic web. Finally, deep and complete galaxy survey of the local universe is mandatory for better prediction of underdense region. So that is all of my talk. Thank you for listening.